How does dividing the speed of light by chocolate chips give you the frequency of the microwaves being produced by your household kitchen microwave oven? Stick around and we're going to find out. And yes, when you're done, you can totally eat all of these chocolate chips. Party bonus. In physics, there are a lot of famous equations. Everything from Sir Isaac Newton's second law of motion, which states force equals mass times acceleration. By the way, we did a video on that law when we were shooting model rockets way back when our channel started, so you can go back and check that one out if you're interested. There's also the Graham-Poobah physics equations discovered by Albert Einstein, which is of course the famous E equals mc squared equation. And while we're not going to be studying that one today, we are going to borrow the C from that equation, which stands for the speed of light. You see, the speed of light is pretty fast. It's not 3 meters per second, 300 meters per second. It's actually pretty close to 300 million meters per second. And if you do the math, that comes out to about 186,000 miles per hour. So the slightly less famous equation that we're going to be studying in this video is the speed of electromagnetic waves in the UV spectrum equals the wavelength of the wave times its frequency. And more importantly, today we're going to be focusing on frequency, what it is, how it's defined, because we did wavelength in last week's video. Again, check that video out first. Basically, in last week's video, we used cheese to help us visualize the actual size of the electromagnetic wave that our household microwave oven was producing. And that's the crux of this week's video. If we can figure out the wavelength of the electromagnetic wave that our microwave produces, and we also know the speed of the wave, then we already know 2 of the 3 variables in our equation for this week's video, which means we can easily figure out the frequency of the wavelength being used by our microwave. Very similar to last week's experiment, you're going to want to take a microwave-safe plate. Instead of using cheese like we did last time, we're going to line up a row of chocolate chips on our plate and place it into the microwave. Remember to turn the turntable off in your microwave if you're able to, or all you have to do if your microwave doesn't give you that option is to remove the spinning glass plate at the bottom of your microwave before we get started. And then we're going to cook the chocolate chips for about 20 seconds. And just like the instructions say on your favorite Hot Pocket box, based on your microwave's power, your cooking time may vary. While these chocolate chips are warming up in the microwave, let's take a second and talk about frequency. Last week we talked about the wavelength of the wave, and how if you went from one crest to one crest or one trough to another trough, that would give you the distance of the wavelength. And in the wavelength that we drew here, you can see that from crest to crest or trough to trough is about 5 centimeters. Now, frequency is determined by how many waves pass a given point in a certain amount of time, usually measured in a second. So let's take, for example, our wavelength here. If we put it into motion over 1 second, we can see that exactly 1 wavelength passed over our arrow here. So 1 wavelength per second, that would mean the frequency of this wavelength in this example is 1 hertz, 1 wavelength per second. If we were to speed up the wavelength, however, we can see that instead of 1 wavelength passing over the arrow in 1 second, 4 wavelengths passed over the arrow in 1 second. So that means the frequency in this example is 4 hertz. And an interesting fact, the higher the frequency, the shorter the wavelength, and the more energy overall that the electromagnetic wave has. It makes sense because if you look in these videos where my kids are playing with the Slinky, they're not using much energy with their hands to create a wave. The wavelength is long and there's not as much speed in the overall wave. However, when I try and go in there using more energy, you can see the wave seems to be traveling farther, the wavelengths are shorter, and therefore that's going to give us a higher frequency. That explains why X-rays who have a higher frequency and a shorter wavelength have much more energy and are much more harmful over time than something that has longer wavelengths and lower energy like a radio wave. Essentially what you want to do is cook the chocolate chips just long enough until some of the chips begin to melt, but not all of them. We had to cook our chocolate chips for about 25 seconds before we could see the effect that we wanted. And that effect is when you take them out of the microwave, you're going to notice that some of them have started to melt more than others. And if you remember from last week's video, that those areas that are melted correspond to antinodes in the wavelength, and those antinodes are maximum areas of energy from our electromagnetic wave in the microwave oven. And if we can find 2 adjacent antinodes on our chocolate chips, we know those antinodes represent an adjacent trough and a crest. Because these 2 points are half of a wavelength, what we have to do to get the wavelength from our chocolate chips is to multiply them by 2 so we can get the full wavelength here. And in the electromagnetic wave here, our wavelength was 5 centimeters. But when we measured the adjacent antinodes in our chocolate chips, they measured 7 centimeters apart. We had to multiply it by 2 to get the whole wavelength because of what we talked about here, and it comes out to 14 centimeters. And if we go back to our equation, the speed of light equals the wavelength times the frequency, then all we have to do is some simple arithmetic to figure out that the frequency is equal to the speed of light divided by the wavelength. And because we know the speed of light is roughly 300 million meters per second, and we now know the wavelength of our microwave oven electromagnetic wave is 14 centimeters, or when we convert it to meters is 0.14 meters, all we have to do now is plug it into the equation. 300 million divided by 0.14 meters is a very large number. It's basically, as you can see, 2 to the 9th power. And what's interesting is we can take this number and go to our microwave and confirm it. Usually on the inside door panel of every microwave, it'll tell you the frequency that it's operating at. And in our microwave, like most, and I bet yours as well, it's essentially 2 gigahertz, plus or minus several hundred million hertz. But when you're measuring chocolate chips, you can be afforded a little margin of error. That's it for this week's video. Admittedly, this topic can seem a little complex, but I guarantee you are probably at home going over multiplication tables with your child. So if you're sitting there going 2 times 3 equals 6, 3 times 3 equals 9, all we're doing with this equation here is substituting numerical values with concepts. Substituting 2 times 3 with wavelengths times frequency. I promise you, if you do this experiment with your child, they will grasp the knowledge quicker than you think they will at this young age. One of two things is going to happen. They're either really going to enjoy it and ask a bunch of questions, or they're not going to enjoy it at all and want to go back to doing something different. But that doesn't make it a failure. It means you were just doing your job as a homeschooling parent and exposing them to different concepts. It's just food for thought. Please don't feel too concerned about these topics or intimidated if you don't feel like your children are quite ready for them yet. In the coming weeks, I have some additional ideas that also deal with electromagnetic waves that are a little bit more elementary in complexity. So subscribe to the channel if you haven't already. Have a great day, everybody, and we'll see you next week.